Okay. So hello everyone. My name is Fangzheng Lyu, and I'm assistant professor at Department of Geography of Virginia Tech. So today I'm happy to be here to talk about my recent work, which is looking at the evaluation metrics. So I'm thinking about integrating, assessing the spatial assessment of geospatial in the geospatial AI model, especially the training and also the evaluation. So I would like to firstly talk about the Geo AI model and the general AI model in the evaluation problem. So those are the evaluation metrics that we usually use. So for classification problems, we have usually generate the evaluation metrics based on the confusion metrics, right? So we have the accuracy, we have the precision, we have the recall, and we have the F1 score. So there are more, but those are mostly the tools that we use to evaluate whether this model is performing good or this model is performing bad. So here, this is what we have. Another thing, if we are looking at a regression model, there are other evaluation metrics existing here. So most straightforward, that will be the mean absolute error. So right, so the equation is at the top. So there are a couple of equations. Also the root mean square error, the RMSE is the most commonly used one. If we are talking about diving into the realm of remote sensing analysis or more complex evaluation tools, there are others. For example, the relative dimension global error synthesis, the ERGAS, which is the equation is over there, is a little bit more complex, but they are mostly looking at each pixel, right? So each when we are talking about remote sensing, whether this result is good for the regressions, it look at each pixels in this image and say what are the difference between the reference data, right? So there are something more, for example, the spectral angle mapping, the SAM, the structural similarity index measure, the SSIM. I just list here a couple, but those are the commonly used tools that we have nowadays in the Geo AI model evaluations. So actually, so after looking at this, one thing that drew my attention is I was looking at those evaluation metrics, but one thing I noticed is that all these metrics only focus on the pixel-wise accuracy or the accuracy based on true or false if we are thinking about the classification problems, but ignore the spatial context and the spatial relationship in the geographic data, right? So the geographic data, we're looking at whether it's right or wrong at each pixel, but the spatial relationship or the spatial accuracy is often ignored. So I'm thinking about how can we integrate the spatial thinking in the Geo AI model evaluation, and what can we do when we are moving beyond the pixel-wise accuracies in the Geo AI model evaluation. So the spatial accuracy definitely matters, right? So here we have a lot of interesting and cool concepts in the geospatial, in the geography world. For example, the spatial autocorrelation, the spatial patterns, the spatial context, but those things are not reflected in the evaluation of the model, right? So the Geo AI models, those things are often overlooked. So here there are two case studies I'm looking at to illustrate this problem. So firstly, is a classic classification problems using the deep learning Geo AI model. So here, the question I'm working on is the new building detection using the street view data. So basically, here we have collected massive street view data, in total over 100,000 street view data images from 2007 to 2023 from the Mecklenburg counties in North Carolina, and we aim to use this imageries to look at, okay, whether there is new building construction or there is no new building construction. So image like that is like time series image, as you can see on the left-hand side. So here, this one is example from 2008 to 2021. There are a couple of images taken at the same location at different times, right? So if you look at this from 2017 April to 18th March, there are a new building construction over there. So this is very straightforward problem, right? So this is what we are looking at, is to say, okay, so can we use the GeoAI model, the deep learning model, to detect whether there are major building constructions happenings from 2007 to 2023. So those are the locations where we collect the data. In total, we have in total 3,577 data point getting collected across the Mecklenburg County. So those are a lot of data. Most of the data, so we are collecting the data based on the census tract block. So basically, for each census tract block, we are trying to recruit 10 points. And those 10 points are where we are looking at whether there have been major construction or not. So here, there are two models we have been leveraging. The first one is the vision transformer model. The second one, we are using the convolutional neural network model. So here we are looking at this two model, and this two model is generating actually identical confusion metrics. So that is to say, their accuracy, their F1 score, their recall, their precision, they're all the same. So overall speaking, this two model is good, but if we are looking at a spatial distribution of the misclassification, we can see very obvious difference. So if you look at the figure on the left-hand side, those are new building construction and no new building construction. So about 550 locations has a new building construction, while the other about 3,000 doesn't have a new building construction. But using this two model classification, the first model is indicating most of the misclassification is happening basically distributed across the county. But on the other hand, if we are looking at the convolutional models, we find the misclassification mostly centered near downtown, right? So those are some observation that we have using these two different models. So here, this is make me really interested in this story, because here the model is coming with identical confusion metrics. So in terms of the accuracy or the evaluation of these two models, they should be identical. But in terms of the spatial performance, of course, these two are very different, because one with the most of the misclassification next to the downtown, but others are misclassification across the space, right? So here we have so for example, the spatial autocorrelation problems is talking about, okay, so this two model actually might have a different performance. They have one is better than the others in the spatial context. So we are talking, so we think, so here the geography context, whether this is downtown when we are having a lot of misclassification for the GeoAI model, or the suburban areas really matters here in the model selection. Another case study we have conducted is more towards the regression. So here we are looking at a typical regression models using the deep learning framework. So we are looking at the remote sensing image fusion here. So basically the concept is we are aiming to generate high spatial resolution, high temporal resolution imagery with high spatial resolution, low temporal imagery, and high temporal, low spatial resolution imagery. For example, we have the Landsat data having pretty good spatial resolution of 50 meters resolution, but the data coming every 16 days. But on the other hand, we have the modest data, which is coming back every single day, but the spatial resolution is not that good, about 500 to 1 kilometers of spatial resolution. So here, the goal here is to using a deep learning model to do this spatial temporal fusion to generate image that is of both high spatial resolution and temporal high resolution. So this one is also a very typical geospatial problems, and this geospatial problems often involves the deep learning techniques. So here, the case study we are looking at is actually in Australia. It's called the CIA location. So it is an irrigation area. We are dominated by the rice production and the agriculture production area. And as you can see, the area is a little bit above over here. It's a relatively small areas, and we are looking at this location to see if we can, doing the image fusion, generate a model for the image fusion for that location. So here we try a couple of existing benchmark model for our practice. So those are all deep learning models. A lot of it are based on the generative adversary network structure. So for example, the GN-based spatial temporal fusion model, the GN-STFM, and also the high precision remote sensing spatial temporal fusion model, the HPLS-GN. So those are the generative adversary network structures. We also have the flexible spatial temporal data fusion, the FSDAF model, and also the enhanced deep convolutional spatial temporal fusion network model. So those are all the basically state-of-the-art model that we used for the spatial temporal image fusion. So here we are trying to evaluating their accuracy, right? So here the goal is for us, we replicate their models and we apply on our data set to see, okay, so what are the performance of those models? So here we evaluating the accuracy of it. So we see here, as you can see in the figure at the bottom, we see the FSDAF model perform the best for the evaluation metrics using the RMSE, the root mean square error, and SSIM. And to find the EDC, STFM performed really good for the ERGAS and the SAM. So the question comes to me that which model is the best, right? So here there is a controversy. But one thing we didn't think about or not involved in this model is the spatial accuracy, right? So here, if we are adding the components of spatial accuracy, which are representing by the LBP, is the spatial accuracy evaluation matrix, we find that actually the HPLTS-GAN model, it become the best performing models in terms of the spatial accuracies instead of the spectral accuracy. So here, there are going to be a bigger problems. But if we look at this in overall speaking, we find the EDC STFM seems to be the overall best option considering both the spatial accuracy and also the spectral accuracy. So here, what I want to bring up here in this case study is that the spatial accuracy also should play a big role in the evaluation of the GeoAI model. So here, the best spectral performance doesn't mean the best spatial performance in the GeoAI model evaluation. This happens when we are evaluating the model, but I also think that in the model training or in the model construction, we should also involve the spatial thinkings or the spatial components. So here, another model we have been, so here there are some potential spatial metrics in the model evaluation that could involve, for example, spatial autocorrelation, the local binary pattern, which is the LBP, which was previously bring up for the model evaluation. So those can be added in the spatial evaluation or the model construction. So here, going another step forward, we are trying to integrate the spatial accuracies in the GeoAI model construction. So in the training stage, we are trying to add them here. So here we are adding the spatial loss function for the remote sensing image fusion model. So here we are developing a new model called multi-stream spatial temporal fusion generated adversary network. So the structure is a little bit complicated, but the core focus is we are integrating this spatial loss function in our model building to make sure that the model is optimized towards its spatial accuracy. So this is the model structure. We have is a generative adversary network-based model. So we have the generator and discriminator. So here, this is the result we have. So here we are not in this model, we are not in the model construction practice. We are not only just prioritizing the spectral accuracy, but also the spatial accuracy is involved in the model optimization. So we see here also comparing with the existing benchmark, as you can see on the first top four, the SSDAF, EDC, STFM. So those are the benchmark model. We see there are the model proposed by us has a significantly better performance, especially in the spatial accuracy category. So not necessarily the spectral performance is also good, but it is the spatial accuracy that stands out here in this case study. So here, going back, so here we think that in terms of the evaluation metric selections, of course, we still have the traditional statistical model, but in the Geo AI model, especially if we can add the spatial accuracies into the model construction and also the model evaluation, it will be more optimized towards the geospatial context. Okay, so that's it, and let me know if you have any questions.